and they don't miss anything. So we'll continue like with something very basic, like for machine learning in general. That we, I guess we stopped at the point. Oh, why is I need to have network? Why I need network? This is very slow to move back. Okay, I guess I'm almost there. So remember what we have again. Like, so basically, like, let's say we have some training data. Like we have the most classic, like supervised learning. So let's say we have x1, x2, and so on is training data and have like corresponding outcome. Let's say y1, y2, and so on. So here, let's assume like the x here, the input is like a vector, but y is just a scalar. So, and what we want to train is like some kind of model that with some input x will get me some output y, right? So this model can be, hopefully can be parameterized by some weights, some parameters, let's say w. And so therefore, like what we hope is like for a function like that, we will have like, why I keep, we will have like fxi w is close to yi, right? Something like that. So in terms of like how close they are, like we can use a loss function. Let's say we can define a loss function, just measure how far these two from each other. So we'll say the loss is big if like they are far away. So we say we have a loss function like xi w yi, something like that. So again, like if they are far away, this loss will be big. So
hello, can you guys hear us?
Yes, we are.
This is just Tulsa. I'm sorry.
Yes. Oh, yes, sure. I screencast. We just got started, but like I did a screencast. So in case you want to, but anyway, like just quick, kind of like few words like, of what we are talking about is just like we're trying to set up a model. Like this is like just something, a model that with some parameter w, and so we are going to feed our data with this model. So essentially, like how we're going to fit it is like we want to have the training data for like, let's say we have x1 up to xn and then y1 up to yn, and for each of these input xi, and with the kind of trained parameter, we hope this fxiw will be close to yi. And then we can use a loss function to kind of compute how close they are each other. And more specifically, this loss function can be just a mean square error. Let's say I can set like maybe it's just this defined as, so I use a triangle equal to mean defined as like yi square, something like that. So in that sense, like what we mean by training a model is just trying to solve an optimization problem. So we try to minimize kind of this loss function, right? And actually essentially the sum of loss function, like from I from 1 to n. Let's say if I have n data there, and the loss f xi w yi, something like that, right? And minimize with respect to w. So let's give a concrete example. Let's say we consider, say, linear regression. A regression problem. So regression meaning that like your output will be continuous, right? So can have like continuous values. And so let me give a simple example. Let's say if I want to predict the weight or like the mass of like some people, some person, and let's say I've given the input x, like x is some kind of features. So let's say x contain his height and his BMI and his age, let's say. So just 3 values. And then like I want to predict his mass or his weight. And let's say his height is 1.8 meter and BMI is say 23 and age is 29. And then I have some weights there, maybe, I don't know, maybe 150 pounds, I don't know. And now what we can do is we can have a, of course we need to specify. So basically we now this is the y, right? This is x and this is y. What we want is that we have a model w, that with parameterized by some w here. And I have this x, again, is close to y, right? So for linear regression, as the name suggests, it would be like just a linear thing. So our model will be simply something like fxw defined as just sum over w k xk, something like that. So in this case, k is equal to 1 to 3. And oh, by the way, like I want to also add a bias term, like in the sense I can something like is equal to that add with a bias, let's say b here. But more conveniently, like most people will just absorb this bias into this weight as well. So what we can do is like we can extend this feature with like just height by BMI and age, but we also add a constant here, just a dummy constant here. So without loss of generator, I can just add 1 here. So now the vector, instead of like I have 3 features, I have 4 features here. And then like here the weight will then will be like from 1 to 3 to up to 1 to 4. So essentially this like W4 here is just equal to B kind of. So here. So and then like I can just write it more succinctly in a vector form, right? I can write this something like W transpose times X, let's say. So both of them are vector. So W transpose would be like a 1 by 4 vectors, and X would be like a 4 by 1 vector, right? So this is just a shorthand notation for this guy here. So then let's say I also use a loss function. We mentioned that we need to specify some loss function, right? So we want here, like we have many ways, right? So let's say the first guy, we have like this is like x1 that have y1, the corresponding y1 is, how do I move this away? This is, okay, I can move up. Y1 is equal to, as I mentioned, 115 pounds. Maybe I have a second fellow here. Have like x2 and y2. This is x1. Maybe x2 has like 1.7, 22, and maybe 25, and then like this 140 pounds. I made up these numbers apparently. So I have many of these, right? And then now this is my x1, x2, and x3, also y1, y2, and so on. As I said, maybe I have n of them, like up to xn. This is all vectors now, and this is what, up to n here. So I want to have like this x w multiplied by x I will be close to this y I, right? So in terms of closeness, again we can use the mean square error. So then it's basically just w transpose times xi minus yi square this to be small. Basically, we hope this to be small. So the loss function basically loss. This is actually basically loss w transpose xi and yi. So just my loss function again. I use a square error. Now what next? So then I basically okay. Then what we want is if we want to fit this model, we are trying to look at all the data, right? I is from 1 to n, let's say, and we want to minimize over w. Right? That's what we want. And so now let's see. Let's say we the sum over everything, right? But let's look at just one sample here. So let's say if we just have one sample, so if we want to minimize wx transpose minus y, let's say, what's this? So this suddenly okay, here come back. So we can do a little bit calculus here. So note that this is a number, right? Each of these guys is a vector, but like this w transpose multiplied by x is a scalar. So this is also a scalar. So this square, I can rewrite this as a w transpose x minus y. I can put a transpose here actually. And let me put a dummy transpose here. W transpose.
Dr. Shane,
yes.
real quick question on your W transpose. Where is what is W? Where is the W coming from?
W is parameters. So basically, we have a model like a linear regression model here. It's more precise. A linear regression model here is specified by something like this. So for an input x here, so the output like will be just like w transpose multiplied by x. So, but of course, it can be loss of flexibility, right? Depends on like what kind of w you have. So therefore, it depends on what kind of data you have. You want to train your model, or like you want to fit w such that your expected output, like basically w transpose multiplied by x, is close to your I shouldn't say expected output. Your output, like w transpose multiplied by x, is close to your desired output y here. So therefore, like we can we can just compute the square difference, right? So therefore, we want the square difference as small as possible. So that's how. That's what I'm trying to do now. Is actually then we try to minimize this. Minimize this with respect to your w, the parameter here. Yes.
Why should we use W transpose instead of W itself to modify the effects?
Say that again.
Why should we use the W transpose instead of W itself?
Oh, okay. This okay. This is a convention. Is pretty common like among papers and so on. Like typically when we don't specify and when we describe a vector, like we always assume it's a column vector. So it's a sorry about that. It's a convention that is very popular among like engineers and math science. Sometimes like people will swap the convention, but this is most common. People whenever they say vectors, they refer to a column vectors. Yeah. So here W also. Therefore, like W and X is actually same size, same shape. It's all in this case both of them is 4×1. So therefore, like if I want to multiply to get a number, so I need to first get a transpose of W to make it 1×4 basically. Yeah. And then, yes. So, Tosa, did I answer your question? Like, is that clear? Like, what W is now?
Yes, I understand.
Okay, thank you. So now then let's continue. So therefore, like, let's say if we just have one data point, let's assume just consider one data point first. If I just have one data point here, so we're just trying to find W such that we're going to minimize these terms, right? And let me write this as this is just two scalar numbers multiplied with each other, right? So here put a transpose here just for convenience. You can omit the transpose, but it's actually it will be the same. But if I put it here, it looks a little bit better, as you will see. So I multiply this together. So if I do a transpose of this guy, it's y transpose minus x transpose w, multiply with this guy, w transpose x minus y. So it will be equal to, wait a sec, actually, I flip a better, this is not a good order, actually I should flip the other way, it's better. Let's see. Yeah, actually, it's better I put a, let's, yeah, actually it's better I put the transpose here. Okay, it looks like I'm doing arbitrary, but it doesn't really matter because this is just a scalar number. I can put transpose anywhere I want. Yeah, it's scalar because here is a W transpose multiplied by x is just a scalar, right? Yeah, so y is also a scalar. So why I'm doing this, because I want to get something like W transpose x multiplied by something W. Here you see this term multiplied by this term, I will get W transpose x transpose W. And this is like something like W transpose. This I can think of. This is just a matrix, something like some matrix, and taking W transpose with respect to W, this it is like kind of more people used to, I guess. So so therefore I just want to make it this shape. But anyway, let's expand it. Like I'm jumping ahead. Let's just do step by step. So I expand this whole thing. Right, first term is this, and then I have a y W transpose x, and I have a, oh, that's pretty annoying also. Have, oh, no. I need to be really careful. I already do a transpose here. Maybe I just really do a one more step here. Yeah, I can't really do algebra, honestly. This is a x transpose w. So transpose this guy. Remember, if you transpose a b, you got b transpose a transpose. Yeah. And so therefore, like I have like x transpose and then w transpose get back itself, and then this minus y transpose. Okay, something like this. And then so I expand this. I have w transpose x transpose w minus y x transpose w minus, let's say this multiplied by this guy, w transpose x y transpose minus y plus y transpose. Now it looks messy, but this is everything supposed to be scalar, right? Because we know this, we have a scalar, it should be everything is scalar. So this y is let's see. Yeah, y is a number. Y is a number. X transpose is like this. W is like this. Oh, okay. And this should be a number. So this multiplied by this get a scalar, and this multiplied by scalar and scalar. So it look complicated, but remember what we are trying to minimize. We are trying to minimize over W, right? So this, all of this we can consider as constant, like this, and this, like this is a constant. So therefore, like if this just go back to like I don't know, like your first calculus class. So if you try to minimize something, is you're trying to take the gradient. Okay, remember we talked about gradient last time. So we take a gradient of that function. In this case, the gradient with respect to W should be equal to 0, right? So that's what we're trying to do. So we're going to take, and the first thing is that the last term does not depend on W. So this, if we take gradient of this guy, it just gets 0. It doesn't have anything. So let's do, these two terms is actually the same thing, like because this one is equal to y x transpose W transpose, right? Actually, so therefore, like this term is essentially the same thing because it's a scalar. Transpose of a scalar itself. Therefore, actually, I can also write maybe just minus 2y x transpose W. It will be the same thing actually. Is that clear? Like these two guys are actually the same. Okay, so now then, okay, this is something that okay, I will do it one time. So what's the gradient of this guy? If I
Gradient W?
Yeah, in terms of W.
It's just negative 2yx.
Yes. So everyone see that, or like should I go step by step into that? So for example, I have A transpose W. Now if I take the gradient, what does gradient mean? Like if I take partial derivative of Wi, this should give me the ith component, right? If I do the gradient, for example, like basically the gradient will be like this way. Partial W2, A transpose W, partial W3, and so on, A transpose W, right? So, and this guy, of course, this A transpose W is just A1 W1 plus A2 W2 plus so on and so forth, right? So, therefore, taking partial derivative with respect to W1 will give me just A1, right? So, therefore, like the first element is just A1. Similarly, the second element is just like A2, and so on and so forth. Therefore, it just give me back A. So therefore, if I have A transpose W, take partial derivative with respect to W, it just give me A. So therefore, like it should give me, oh, I should be careful. Like it give me Give me A is like, I actually, if I want to be really careful, I should first write this as 2xy transpose. Am I right? Yes. MW, right? What I mean is like transpose of this guy will give me this. I just want to match the form here. So therefore, like the partial derivative of this guy with respect to W is just 2xy transpose, or just actually 2xy. Y is a scalar. Right? Yeah. Yes.
Why you mentioned that the gradient is 0?
Not yet. Okay, I want to set gradient to be 0 because I try to minimize that, right? I want to minimize over W. So it's just like, think of like the simplest case, 1D case, right? If you are trying to maximize or minimize something, so Tosa, is that any question? So okay, for this guy is like this, and then how about this term? This term will be
No question.
okay. So this term will be, think of like x transpose is like just a matrix A. Let's say some matrix A. So I have this like second order form like W transpose A W is like when you multiply it out, it's a scalar. And when I take the partial derivative of if I want to compute the gradient again, I should do something like that, right? If W1 and then W2 and so on and so forth. So just look at the first element to see what we get. Like this one here, if I take, let's expand this. This is what? This is like Wi. Let's see, what is this? AW is let me write AW first. AW will be something like that, right? Sum over A1J. I need more space. I want. Oh yeah. Sum over A1J WJ. Sum over J. And I have a W transpose here, and JA2JWJ. Does it make sense to you? I'm probably not doing something like the most careful. I mean, probably not the most careful thing to do. But I just, when I compute this, let's just do this first and look at what is this. This would be a vector, right? And this would be like a matrix like A. This A matrix would be like something A1. I have an A1 column, like A2 column, A1 row, A2 row, A3 row, and so on. Then when I multiply this by W, A multiplied by W is essentially the first row here multiplied by W. So basically this guy, and then the second element is like this row multiplied by this guy and equal to this, and so on. So then now multiply by W, so it should be equal to W I some A I J W J I J. Okay, so therefore like something like that equal to Wi A. I can pull the summation outside Wj. So this is basically that. So this term is just equal to this. Now if I take partial derivative with respect to W1, what do I have? I will have basically either if I have both I and j that's not equal to 1, then for those terms will be just equal to 0, right? So I will only have terms remaining is say either I equal to 1 and j equal to 1. So and when I equal to 1, then I basically partial derivative with W1, then just have this remaining things, right? This left behind. So therefore I actually have like A1J WJ, right? And then or like j equal to 1, then have this part is left behind. So I have like I1 Wi sum over I. So So therefore, like what we and of course, like what this is like, it looks a little bit. I can make this similar form to this guy. What I can do is say instead of like consider AI1 multiplied by WI, I can think of this as a A1I, but I do a transpose for this guy multiplied by WI. So then these two forms look kind of the same. So therefore, like what I really have is really if I try all the terms here, basically what I have is actually equal to A plus A transpose multiplied by W. This is actually the gradient of this guy. So is that clear? I feel that like maybe I have.
Did you say this was a model for a single neuron? Is that what it is?
Oh no, we are doing linear regression, so it's the model is a simple linear regression that like your output is just equal to your features times the weight, basically projected to with the weight. So or precisely is this guy here just equal to W transpose multiplied by X. So and actually for new one, what's going on is later on is the only difference is that you add the activation function here, but here is before you add the activation function. So okay, I guess you go too far into this, but this is just kind of algebra that if you. But I think like you should be able to do this honestly. So it kind of help your understanding actually. So any question like this looks a little bit complex, but it's actually not. Especially like what you need to do often is like you just need to once you see this several times, of course, then you know that okay, if I have W transpose A W, I take a great partial derivative of W, I know why that way it should be like this. Like if you do it several times, you know that okay, this is we have a formula like that. But it's good to know where it comes from, basically. So, but then I guess this is a kind of messy. I mean, I just erase some of this. So then, as I said, like therefore, actually, what we have is when try to minimize this W, or like we try to take the gradient of this guy. What we have here is actually just X transpose times W plus X transpose times W. That's taking the gradient of this with respect to W plus YX. Sorry, it's minus YX. Actually, it should be minus 2YX here because I have two of these terms here. And I want to set it to 0, right? So I have that. So this transpose of this guy is basically just this thing. So this also got two of them, 2X transpose. So the two get cancelled here. So what I have is really just X transpose multiplied by W minus YX is equal to 0. Okay. Or YX I can weigh XY as well. Y is just a scalar. So therefore, like what's W? Then W is just equal to XY XX transpose inverse. So this is like the you probably see this before. It's just a pseudo inverse, like when you do a linear algebra trying to minimize when you have a kind of a set of equations, and you find the weight to kind of solve the set of equations and get the approximation of that when the number of equations is more than your basically more than the number of unknown. Then okay, I probably shouldn't say even though it's just it's not related to. But anyway, this have a name for that is a pseudo inverse. Yeah. So and but in this case that's very nice. What I'm saying, like this essentially have a closed form. You know precisely what is the optimum weight there. So and because of a closed form, it can be really quick when you need to train a model like this. And go back to our example here. So we just said at the beginning, this example is trying to fit some of these personal like health data, like weight or not weight, height, BMI, and so on. I'm trying to estimate the actual weight. Of course, you see, like by design, I am making things up that it doesn't. Some of the features is kind of useless. Of course, you know that like if I know the BMI, I know the height. Most likely, if you know the definition of the BMI, basically like BMI is actually is equal to the mass over height square. So in this case, this is a kind of like a dummy problem. Like one of these features is actually useless. The H here is useless, but we just want to see like how good it is. Like if we do something like this, like see if the model is able to realize that okay, this is a useless features that I don't really want to use that. And so let's do some experiment. So let's go to have some of this actually. So let's say I made up some experiment here. Like I have some synthetic data, like 30 training data points, and I wiggle the mass a little bit. Like so, given my height and BMI, basically I will have the exact mass, right? But here I just add some Gaussian noise there. Let's say a standard deviation for the Gaussian noise is 3 kilograms, and then and then I train it. I got some training weight like this. I have 4 of this way. So basically, if you remember, we have earlier the features are, let's see if I remember correctly. Are the height and then the BMI, and this one is the age, and this is just a dummy, like it's a padding is just 1. So you can say it's kind of nice. Actually, I have written here actually. So it's the model did something like reasonable. Basically, for the age, we know it's kind of like useless. So therefore, like the weight correspond to the age is like actually very small compared to the others. And the mean square error with this is equal to this. And so let's say if we can reduce this error a little bit. So how can we reduce the error? What? No. In this case, for this model, it's already optimum, right? Because you find you have an exact solution for the weight actually. That one is already optimum.
Reduce Like times 1.5 to the, it's called like I don't remember the term in this here, it's called like regulation.
Say that again?
Like just reduce biases.
Oh, okay. This is you're thinking the bias. Okay. So reduce bias. Yeah, you're right. That one is bias. Like here is bias. So we're biased because the model is not complex enough. Complex enough. So what you're suggesting would be like increase the complexity of the model. So along this line, okay. Now I want to keep this linear regression model, so it's kind of neat, simple, and you have the solution is exactly because there's an analytic solution. So as I mentioned, you have basically the weight is precisely equal to this, so it's a perfect exact. So what we can do to increase the complexity a little bit is we can add more high order feature. So it's the what people kind of sometimes call this kernel trick, right? So it's like this is not precisely kernel trick, but it's like have the same flavor. It's like you map your feature from lower dimension to higher dimension. So in this case, it's like you just add more features. It's just like the same thing, but you kind of like add combination of your feature. So in this case, it's just the square of the features, let's say, and also the product of the feature, let's say, and keep trying to connect here. And so more precisely here, I add x1 square, x2 square, and also the product between the cross feature like x1, x2, and so on. So then with that, like I have this is my new features, my new set of features. Then I can do the same thing, right? This is my new x basically, right? And I can try to do the regression again, and I know the solution again, right? The solution again is kind of exact, right? So just the weight now is longer now because previously the dimension of this x is just I have 4 elements there. Now I have basically after this expansion here I have 6, 10 now, I think. So and then okay, I can do the same thing and compute the mean square error. Now it goes down. Apparently, it goes down. And of course, I can repeat this, right? I can put like even higher order features. So maybe like x cubed, and I can now the model parameters further increase. Like it increased like 4 to 10. Now like the size of the model like from 4 to 10 to now 25. And mean square continue to drop, and I can continue to increase that. Like 4th order, it will go to 70s. So, but what's wrong with that? Like, seems like it's like I have like free lunch here. So, is there something wrong here? Yes. So I'm only showing you this is a training error, but if you look at the test error, it's not really doing so. When I increase the when I first expand that like from 4 number of parameters from 4 to 10, I do have drop for both like training and testing error, but after that like my testing error just goes up. So I'm actually it goes up drastically, like from 3 to 4 is actually like it's totally out of the track. So I guess the classic example to illustrate that is just think of curve fitting. So this now looks at another problem like a simple curve fitting here. I have just a function is I have trying to fit let's see. So I have some data here. I just try to fit this. So, and of course, if I linear regression is basically just a fit a line here, right? This is my result. And then I can repeat the same thing what we did earlier. So I can expand the feature with higher order. So originally, in this case here, the number feature at the beginning is just 1, right? Because it's just 1 dimension, just fitting a line. So the input is just the x coordinate. I try to estimate the y coordinate. So now if I expand it like 1 time, then I will expand my features from 1mx to 1mx mx squared. Then again I can do what I did earlier and compute the weight and do the estimation, and this is the estimation we got. And I can continue again include higher and higher order, and as you can see, as I include higher and higher order, of course if your data is completely noise free, then it won't have this problem. But in reality, every data will have noise, right? So I just fit into the noise rather than fit into the data itself. As you can see, if I go up to 6th order, my curve fit really well with the data. But the problem is it's actually far from the ground truth there. This is the same thing. When I increase the capacity of the model, my training errors always goes down, but the testing error doesn't necessarily to go down, and sometimes it goes back up. So that's, as he just mentioned, that's overfitting. And that's also the kind of a trade-off between bias and variance. So when people say it's high variance, is basically your model is overly complex. That I try to memorize these 2 terms this way. So if you say a guy is highly biased, then he's very rigid, he cannot learn anything, right? So therefore he always stuck with that. So you have a model is like this. It doesn't fit into that model. It's a high bias case. Other case, high variance, it doesn't have a stand basically. You give him any other data, it just take all data literally. So then he basically his model in his head is just keep varying in a big way. And so this is a quick summary of some kind of, I guess it's trying to give you a very simple overview of machine learning, because I guess this captures many concepts in machine learning. It's basically what machine learning does eventually is just trying to fit data. You fix a parameter. It's always like this. You fix a model. The model itself can be parameterized somehow. Then now you have some data. At least for supervised learning, you have your input data and also your expected output. Then you're just trying to minimize the loss between the actual output you get with whatever your parameterized model from the desired output, right? So therefore, it's just an optimization problem. But how to solve that optimization problem is another story. Most of the time, as he just mentioned, it's always just gradient descent, because very few models, except for these classic toy problems, we have a excess solution that you can. I just write down the closed form solution, and for more or less all the other models, we just need to go for some numerical method to optimize that. And of course, we don't want to underfit the model, so we want the model have reasonable complexity, can actually learn the data, but at the same time we don't want to overfit that. It's all about generalization, right? So machine learning is all about generalization. The training error, training accuracy doesn't count. It's all the testing accuracy. So you want to be able to, after you train the model, you're able to generalize to to data that you get in the future. Yeah, that's I guess many of you heard of outcomes razor. We don't want the model to be overly complex, but I don't know. This is classic materials, and this completely hold what I talked about like 10 years ago. So people have a different opinion nowadays. Honestly, some people will consider it doesn't matter. Like we never overfit the model, so we just need to add regularization. So that's exactly what deep learning is doing, right? You have as complex model as possible, almost. Of course, you can make it even more complex, but you definitely have a model much more complicated than like whatever models in the past. But then you just have to impose good regularization. And we will talk quite a bit more about regularization in the future. But this is like people agree upon like pretty much like 10 years ago. But nowadays, they talk a little bit less about like versus bias, because like most of the time you just try to get as many data as possible, and then just impose sufficient regularization. And it doesn't matter your model is kind of like very complex. That's the I just mentioned like high bias with high variance. So basically, classically, it kind of like referring to whether your model is like overly complex or overly simplistic, simple. And then that's just okay. I don't know that I so quickly already go into regularization, but it's like just some simple regularization. So if we think of like what we did earlier, so what regularization is like my way of thinking of that. Like okay, actually maybe I should get some opinion from you guys, because I know many of you actually have taken machine learning or similar courses before. Like, what do you think like regularization means?
I think of it in math terms, like your function is going to be differentiable.
That one I don't buy. Okay, well, because let me think of a counter example.
It's just like making this model more accurate than the regularization is like making the model like more accurate than before.
The model doesn't change. Okay, I think it's they change the training process somehow. So any other opinion like? I don't know. I tend to think that okay, regularization is just like trying to make things not very crazy. I'm not sure that make any sense. But what I want to say again, like the model doesn't change, right? When you train after imposing a regularization, so you still have the same model. Basically, you don't change your model, but you typically what you change is you change your objective function. You change, for example, like in our example just explained earlier, we have this linear regression problem. So rather than just trying to minimize the loss only, we're trying to add an additional term to modify the objective function. So often in this kind of like modification, what they add is like they try to make the make the model less. What should I say that? Less active. I'm not sure it's a right word about that. So if you think of like the model, the parameters is like, if you think of the parameters can jump back and forth think of like you're boiling the parameters like on a pot, and then like the parameters just jump back and jump out like I don't know, water or beans or like just jumping. So regularization is like I try to make them not as active, like so I kind of like lower the temperatures somehow, like so they can still change, but they cannot change as much as they originally are able to. So in this case, for example, if this so-called like ridge regression, that I basically just add a term kind of to a penalty about the power. You can think of the power of the parameters, right? Because this is just essentially the sum of squares of all these parameters, right? So you can think of this the power of the parameters, and so therefore, like if I add this to the objective function, remember what we want for this objective function is want it to be small, right? So this will be a penalty. Like I don't want these parameters as big as it's supposed to be. So then, like I have this ridge regression thing, and the nice thing about ridge regression is apparently this guy is same shape of this way. If I expand that, I also have a term like something like W, as you remember earlier, have something like W X transpose X W, something like W transpose X, something like this, and this can be grouped into this guy here. So therefore, I will have something like this, and previously we know that like if I take derivative of this guy, I can solve for W, right? And for the same thing, like I group this term, I take the gradient is just equal to this. Right? Now here we say that like take gradient of this guy is just AW, right? Here is therefore I instead of earlier I have like X transpose, I have X transpose plus this lambda I here. So then again the solution is kind of exact. So it's just have a slight modification like this. So that's why it's very very neat. Again, like another under kind of like exceptional toy problem that have a closed form solution for your parameters. There's another kind of regularization is known as lasso. So in statistics, so what you can look at here is say this is essentially a second order like penalty, right? So we sum over like Wi squared, like sum over the square terms of each of the parameters. But we can sum over the absolute values of each of the parameters. So this gives you a different characteristics and favor. And that's why I kind of don't agree with what you said, because this custom apparently is not differentiable. Yeah. And ideally, actually, people even want to about 10, I'm not sure that you guys heard of that, like compressed sensing, like 10 years or so ago, like it's actually a very popular area in signal processing. It was the area in signal processing like 10 years ago. Like everyone was jumping into that, working on like compressed sensing until it just, okay, it still work, but what I mean is like now the old library is working so much better than those, and then like every people, I mean, just walk away for those algorithms. So but the argument at that time is like they want to add some penalty for the regularization, and ideally what they want is they want to think of this. You want to regularized in such a way that you have a so-called sparse representation. So you have a parameters here. In general, all the parameters can be non-zero. Any of the parameters can be non-zero. But I want to have a sparse kind of like model in the sense that like most of the parameters will be equal to 0. So how can I enforce that? I can impose a so-called zero norm. So this first norm is just something the absolute value, right? The so-called zero norm is just saying that if the value is non-zero, I will count as 1. If it's 0, I count as nothing. Then I just simply count number of non-zero elements there. And actually, this is theoretically it's very nice model because of course this can hook up with anything. You can have any model, you add the zero norms there to try to penalize the model, because once you add the zero norm there, it's basically saying I need the model to be sparse. And this is a really strong regularization in a sense. But in practice, no one can do zero norm. This is not computationally feasible. So therefore, it's always like jump back to this first norm here. Because first norm is a better approximation of zero norm than the second norm that give you closed form. So therefore, like lasso, of course, was invented for many years ago. Like instead, I don't know this history, but at least 30, 40, I don't know how many years, but probably in 60s or 70s. But this kind of like regularized, sparse model idea just came back like in late 90s to mid 2000, and even late 2000. Like, but of course, so not late 2000, late like 2009, 2008, something like that. But then suddenly neural ledgers started to come back, and people suddenly, especially have this image-led challenge after 2012. Then everyone just, give this up and forget about this, and then So
Professor,
yes.
With your regularization methods that you're using, how do you determine a reasonable value for lambda in the equations?
Yeah, that's a very good question. Actually, we don't know. That's typically the case. So oftentimes it's case by case. This is so-called those hyperparameter. It's similar to the same situation of the learning weight when you're trying to train a neural network. You just test it. And it's basically an art. Like you put it per problem, you put it there, see if it works well, then you stick there. Otherwise, you move in another number. So it's a very good question, but unfortunately, there's really no very good solution for that. And of course, but this lambda, of course, is also a hyperparameter to tune the strength of the regularization, right? So if you want to have a stronger regularization, you can increase that. If you want it to be weaker, then you can decrease that. And this is, as I mentioned, why people are interested in that, even though it doesn't have a closed form solution. So it's not like which regression you have a closed form solution. This one doesn't have a closed form solution. But this is a very kind of like classic model. For example, like it's included in the scikit-learn library. So if you use Python, then this is like kind of like a very simple machine learning library. So I don't know, I didn't, but I assume all of you guys know Python well, because the assignment will be like many of them in Python, so you need to know Python well. So, and also, as I mentioned, why is people got interested is that the buzzword like comparisons, but it's already kind of obsolete now, like at this time, at this moment. So this is just an illustration. If I add regression, I add regularization there. Actually, this one, my ridge regression doesn't do that well, but lasso is doing pretty well. You see, like I have I have like ridge regression is still kind of overfit, but lasso is like kind of fit pretty well to the original curve. I guess it's lambda is again like, as you just asked, like, well, how should I pick lambda? It's tricky, like, but you see, if I change lambda, it'd be like you just have different. Of course, like, the reality is like you don't know. So therefore, like when okay, I guess I didn't mention. Typically, when you're trying to use machine learning for a problem, that's why you always like split your data set into several different portions. Like you always have a training set, and then you have a depth set, typical development set, or like what's the other way to say? No. Test set, training set, and suddenly I forgot. Like, but it's like some people call it depth set and a development set, but that's a better word for that, I think. So your test data, typically you don't touch it like until very last moment. When you are done, everything is fixed, everything confirmed. Then you pull out the test data just to test like how good is your model. You don't touch it. Then you have the development set. It's like tune all these hyperparameter. So you are not sure like which lambda you should set. So you just have your training set, like train your parameters, then use your development set to kind of like test all the trained model that you have earlier and help you to select the right hyperparameter. In this case, for example, you select the right lambda there. So, for example, in this case, I should have keep some of these data points. Assuming I have many data points, I have some of the data points. I leave it to fit this curve, but I have some data point will help me to verify whether my fit model is close to the actual data point, and I will pick the lambda that's give me the best result. So this is this conclusion, high bias, high variance, we say that again. And again, it's all about generalization. And for supervised learning, we have classification and regression. And I mean, if you think of supervised learning is nothing, but it's just like minimizing some loss function. You have some fixed model, some parameters you can tune, and then you define a loss function, and then like trying to minimize the loss function with respect to those parameters. Yeah, regularization in terms of my own word, I would say like I'm just trying to make the weights doesn't run wild, so it's like try to make them less active somehow. Is the trend is basically like we always use more complex model, but try to regularize the model. So now no longer people will try to think that we overfit, therefore we try to look for a simple model. It probably is not a very good idea. But instead, like if you think you overfit, you will try to impose some regularization to see if like you get a better result. So that's my introduction of machine learning. We're done of this course now. So we will come back next time to get into some material on neural network. And see you guys Thursday.
Professor, can you,
Yes.
Next time, can you send us your meeting room just a few minutes early for Tulsa to be able to join, so we can join on time?
Oh yes, sure. Like it's sorry, I was a bit late today. Yes.
Yeah, we just need a couple of minutes to get the Polycom system joined to Zoom. So if you could send us your meeting number just a little early.
Yeah. Yes. The tricky part is I don't know how to kind of what is that reserve that meeting. Like always I need to set it up, then I send the. But I guess once I get an email list from you guys, it should be easier. So next time should be faster. So I'll try to send you like 7 minutes earlier.
Okay, thank you.
Yeah, sure.
How can we get these two data? Like where's the -1?
This is the inverse, yeah.
Why is it used?
Oh, yeah, you move there. This I set it to 0. Then this I move to the other side. And then I want to find a W, right? Then this is basically a matrix, right?